In this section, we introduce seasonal ARIMA models. They behave similarly to non-seasonal models, and a lot of the methods that we have been using to fit and work with non-seasonal models will work fine with seasonal models as well. The difference is we have another part of the model which describes the seasonal nature of the series. So up until now, we've talked about ARIMA PDQ models, where the P and the D and the Q describe the non-seasonal part of the model. We're now going to add a section with uppercase P, D, and Q to describe the seasonal part of the model. And a little M on the end says how many observations there are per year. So 12 for monthly data, for example. So whenever I'm using an uppercase letter, I'm talking about the seasonal part of the model. And if I'm using a lowercase letter, I'm talking about the non-seasonal part of the model. So let's look at an example where it's an ARIMA 111-1114. So all of the non-seasonal things are 1, all of the seasonal things are 1, and it's for quarterly data, so m equals 4. And I'll leave off the constant just to keep the equation slightly simpler. So if I write it out in backshift notation, it looks like this, where this first term here describes the non-seasonal AR1. So that's the P equals 1. The next section describes the seasonal AR1. So that's from there. Then we have the non-seasonal difference, lag 1 difference. So that's from here. Then we have the seasonal difference, this bit, and that's from there. That's capital D equals 1. Gives us the seasonal difference at lag 4. Then we have the MA part of the model, the non-seasonal MA1, which comes from here, and the seasonal MA1, which comes from here to give us that last term. So when you write it all out, it looks sort of complicated, but if you look at each of the different sections, you can see that they're just simple little expressions describing, with only one parameter in this case, because all of the values are 1, and describing, is it an MA part or an AR part, and what lag is it? If you expand that out and multiply it all together and then write it in subscript notation, it looks like that, which is way more complicated to read and understand. It doesn't at all look like a ARIMA 111-1114 model, because you can't sort of really untangle all of the pieces. So generally, we like to write it in this backshift form because it's easier to see what's going on. Now, just as with the non-seasonal models, you can look at the ACF and guess an appropriate moving average model, or you can look at the PACF and guess an appropriate AR model. You can do the same with these seasonal models, except you only want to look at the spikes that are multiples of the period. So if it's monthly data, you want to look at the spikes of multiples of 12, so 12, 24, 36, and 48. If it's quarterly data, you'd be looking at spikes at lags 4, 8, 12, 16, and so on. And they have exactly the same interpretation. So if you look at the last significant spike in the ACF on the seasonal lags, that gives you the seasonal MAQ order. If you're having a moving average model, if you're going to have an autoregressive model, you look at the last significant spike in the seasonal lags in the PACF. And then, of course, there's also an automatic way to do this, which is a variation on the algorithm described a couple of sections ago. So the algorithm is exactly the same. There's just a couple of little extra bits. So the first extra bit is it's choosing the capital D by looking at the strength of seasonality. And if the seasonality is strong enough, then it will do a seasonal difference. If it's not strong enough, it won't. So D is equal to 0 or 1. It won't try any other values of capital D. And it'll do the seasonal differencing before it uses the KPSS test to decide whether it needs to do any non-seasonal differences. And then selecting the values of capital P and capital Q are done in exactly the same way as selecting lowercase p and lowercase q. It's just doing variations on the model. And it's using a stepwise search. Okay, so very, very straightforward once you understand the non-seasonal automatic ARIMA algorithm. Okay, we're going to do a couple of examples in this section to illustrate some of the things that happen and how you might use these tools. So this example is employment in the United States in the leisure and hospitality industry since 2000. So the year is after 2000, so the first one is 2001, and we're turning it from thousands into millions by dividing the employed number by 1,000. So you can see what it looks like there. Very strong seasonality and a bit of trend. So looks like we're going to need a seasonal ARIMA model. So first up, let's try differencing at lag 12, because that's the seasonal lag. So we take a difference at lag 12 and have a look at what we see using the GGTS display function, so we can see the ACF and PACF and the time plot all at the same time. And that's also clearly non-stationary, it's wandering around. So although the seasonal difference has removed most of the seasonality in the data, it still has some non-stationary behavior. So we need to do another difference as well to make it stationary. So here we are doing the second lot of differencing. So you see in the code, the first difference here is at lag 12, and then we pipe that into difference. So it'll do a non-seasonal difference, a lag 1 difference. And now this looks pretty stationary. It's sort of wandering around 0. There's not any sort of obvious major patterns going on. And the ACF and PACF both, although there are some significant spikes, you don't sort of have a long decay on the positive side, which is typical of non-stationary data. It also means that we can now have a guess at a model. So we've done 2 lots of different things. So little d is 1, capital D is 1. And if you look at the seasonal lags only, so at 12, 24, and 36, so we're looking at these lags here, which are conveniently labeled on the axis so you can pick them out. There's not, all 3 of them are significant on the PACF side, so it's not sort of easy to pick a seasonal AR model there. On the ACF side, you've got 1 significant spike here at lag 12. That one's just not significant. That one's just not significant. So possibly you'd pick a seasonal MA1 but as part of the model. And then if you look at the non-seasonal lag, so everything up to lag 12, you've got 2 spikes here and you've got 2 spikes here. So you have a choice, either a non-seasonal MA2 or a non-seasonal AR2. Both would be okay. Either would be okay. You don't want them both. You don't want P and Q set to 2 just on the basis of these graphs. You have to choose either to use one or the other. So here are the possibilities. The little d and the capital D were 1, set to 1 because of the differencing. The seasonal MA1 was set, so capital Q was set to 1 because of the seasonal spike in the ACF. And then I couldn't decide whether to do a MA or an AR model. So here's the MA model there, and there's the AR model there. So I've got an ARIMA 012011 as one possibility, and an ARIMA 210011 as the other possibility. And then I'm going to let Fable go and do a whole lot of work. So I'm going to say, you choose a model now, but I'm going to set stepwise false so it does searches a much bigger part of the model space. I'm also going to turn approximations off, which slows it right down, but I've got plenty of time. And I wanted it to actually look as hard as it can to find the best model. And it's come back, and it's, after all that work, it's come back with almost the same model as I came up with. The only difference is this one here. It's come back with a seasonal AR1 parameter as well as a seasonal MA1 parameter. So a slightly different model, but otherwise it's pretty similar to my second guess. Then we can have a look to see how well these models fit. And you can see that the automatically chosen one does quite a bit better. 780, minus 780 is better than minus 776. And that model is slightly better than the other one at minus 775. Okay, so we've got a model now that we've tried some of our own. We've tried the automatic search. We've found one that looks like it's going to be okay. So now we look at the residuals. So we plot the residuals for that model, both the time plot and the ACF plot and the histogram. And the first thing to notice is we've got a bit of a spike happening here at lag 11. So one outside, one off the seasonal lag, but it's and only 1 out of 36, so maybe that's okay. Let's see if we do a long box test, how it goes. So we'll do a long box test. I'll take 24 lags, so 2 years, and I'm going to use degrees of freedom 4 because this model has 4 parameters. Just to remind you what the model is, it's this auto model. So there's 2 of the parameters plus that one makes 4. So if I do that and I do the p-value, it works out fine. So this model is a good model. That little spike outside at lag 11 was not enough to tip it over into the significant region. So I'm pretty happy with that. Now that I've got a model, I can do some forecasting. And so there's the forecast from this model, and it looks great. You might wonder, where did the trend come from? Notice that it's trending upwards. That's because there was 2 lots of differencing. So whenever you've got 2 lots of differencing in a model, you're going to get some trend happening. You don't need the intercept in there. You're going to get some trend happening regardless. The double differencing will induce that. This time there's little d is 1 and capital D is 1, but together they constitute 2 lots of differencing. And the seasonality has picked up the shape, particularly towards the end, pretty well. Okay, let's do another example, a little more complicated one. So this time I'm going to take the corticosteroid drug sales for Australia. So this is ATC2 group HO2 in the PBS dataset. I'm going to summarize it over any other keys that are in the dataset and then divide the cost by 1 million so that I've got it in millions of dollars. So there's a plot of the data. We've seen this data previously in the book. So it's total cost every month on corticosteroid drugs in Australia. That is the cost to the government because the government's subsidising sales. And it's a little bit of change in the variation. So that variation there is a little bit bigger than the variation down here. So taking logs makes it slightly more even. So that's the Box-Cox transformation that we'll use. And then because it's seasonal, we'll take a difference at lag 12. And there's the difference at lag 12, which is now closer to stationary, although you might argue that it needs another difference, or maybe you wouldn't. So it's a little bit subjective at this point whether we want to do the next lot of differencing. I'm going to say no, let's not do the next lot of differencing, but I understand other people could have made a different choice, and maybe on a different day I would have made a different choice. So let's not do the second lot of differencing. So we've just done a difference at lag 12 on the log data. Here is the time plot and the ACF and PACF, and I'm looking to see what might work here. So starting off with the seasonal lags, I've got a lag 12, a lag 24, and then nothing. So the last one there is the 24. But on the ACF side, there's no significances at all in the seasonal lags. So that suggests maybe an AR2 on the seasonal side. And then I look at the non-seasonal part of the model, and I've got these 3 here. Again, on the PACF side. The ACF side is more complicated and it gets quite long, like way out to lag 9 there. I don't want to have a model with that many parameters at this stage, so I'm going to choose the AR3 because it's simpler on the PACF side. So that suggests that we'll take capital D equals 1, little d equals 0. I'm going to have an AR2 on the seasonal part of the model and an AR3 on the non-seasonal part of the model. So overall, I get a 300,210 for monthly data. Okay, what are we going to do with that? So we'll now hit that model along with a whole lot of variations of the model to see what works. So here's some of the variations we've tried. there's the model that I was guessing from those plots. And here's some of the other variations. I'm just changing the numbers by 1 or so every to make relatively simple models. You can see the best of these is actually 301012. When you do this, you have to be careful that you're not comparing models with different levels of differencing. So the little d and the capital D have to be the same to make the comparisons of AICC statistics make sense. If you're comparing models with different types of differencing, then the likelihood is being computed on a different number of observations, and your ARCC statistics are going to not be directly comparable. But for this lot, they're all the same, so I can pick this model here as the best of the models, 301012. So let's fit that model. So I'm taking the log of the cost. I'm not fitting a constant, so I just say tilde 0 to say no constant. And a 301 and a 012 comes back with this model. And then I can have a look at the residuals. There's the ACF plot. Nothing too concerning there. There's a couple of largish spikes, but nothing very far outside the limits. If I take the Lung box test, and I find that it's actually significant, 0.01, so less than 0.05. So there's something about this model something about the data is not being captured in the model. There's information left in the data. There's significant correlations left in the residuals that I'm not capturing in the model. I could still go ahead and do some forecasting. They probably wouldn't be too bad, but let's see if I can find something better. Okay, so let's let Fable go ahead and find the best model it can with no constraints imposed. And it comes back with a 210011. Now, notice it's done a second lot of differencing. So little d is 1 and capital D is 1. So I chose to only do seasonal differencing. It's choosing to do seasonal and first differencing, which means that the AICC statistic is not directly comparable to the models that I had up before. But we can still have a look at this model and see how well it does. Let's look at the residuals. They look a little worse than what I had before. Let's do a Lung box test. This model has 3 parameters, so I set degrees of freedom equals 3, and the p-value is worse. It's 0.003. So this model's not doing so well in terms of capturing the information in the data set. Okay, what next? Well, I've picked one by hand and it didn't do so well. I picked one completely automatically and it did a little worse. So let's use the power of computation and make it work really, really hard. So I'm just going to say, fit an ARIMA model to the log cost data. No stepwise, so look as far afield, look a bit further afield. No approximations, and look for quite big models. So I'm setting p plus little q plus capital P plus capital Q less than or equal to 9. So we can fit some quite large models. And it's come back with this model, which has got 9 parameters. So it's at the edge of the parameter space. And the ARCC statistics slightly better than the other one, the other automatically selected one. Okay, so let's have a look at the residuals for this one. They don't look too bad. I have 9 parameters in this model, so I have to set degrees of freedom equals 9. And it comes back with a p-value of 0.1, which is the first one I've found that is better than 0.05. So the first one that passes the test. Okay, so I've now fitted 3 different models, well, more than 3 models, but I've tested 3 models and I've found one of them at least passes all the tests. Let's now see how well these models do if I use a training set and a test set. So previously I was just fitting these models to all of the data. Let's suppose I only use the data up until June 2006, and I use the next 2 years of data to see which of the models works. So I'm going to use all the models that I've just looked at, the ones that I chose, the automatically chosen ones, and some variations on them. I can do this comparison because I'm not using AICC to do the comparison. I'm going to use root mean squared error on the test set. So therefore, it doesn't matter how many lots of differencing I'm doing. the test set comparisons are still going to be valid. The only thing that I can't do is compare AICC statistics on the training set if I'm using different lots of difference in. Okay, so here's the top few of the models. I tried a lot more than this, but here's the top few of the models that I just fitted. And this is root mean square error on the test set. So if you look down here, you'll see the one that I picked initially down the bottom. You'll see the one that somewhere in there is the one that we ended up picking based on AICC statistics, was that one. This one is slightly better based on root mean squared error. Wasn't so good on AICC statistic. This is the one that down there was the one that we fitted after an awful lot of computation. It's doing a little bit worse on the test set here, the 2-year comparison. So then you have to make a decision. Which of these models are you going to use? So I'm going to take the second one here because it was the best one based on AICC statistics on the training set, on the whole data set, and it's the second best one, very close to the best one on the test set. So it does pretty well everywhere. Thing to notice about that table is that models with low AICC value also tend to give better results when you do out-of-sample testing. Makes sense. AICC is asymptotically equivalent to getting one-step cross-validated forecast errors. So it's equivalent to finding the best model for that purpose. You do have to be careful with AICC comparisons that they have the same orders of differencing, but root mean squared error on a test set or anything on a test set can involve models from anywhere. You don't have to make sure they're consistent. And sometimes you end up choosing the best model, even if it doesn't pass all the tests. And so you'll notice when I said I'm going to use this second one, that was one that didn't pass the Lung box test on the residuals, but it seems to be doing well in other ways, and I'm going to use it even though it didn't pass all the tests. So we'll take that model and we'll produce some forecasts. And the forecasts look like that. And you can see they do pretty well. It's picking up the fact that it's flattening off at the end. And so there's not any clear trend going on in the series. It's the size of the prediction intervals sort of look believable, what might happen in the future. So I'm pretty happy with that result. So that's a couple of examples of using the Fable package to do seasonal ARIMA modeling and some of the things you need to think about when you're doing that.